This is the gravity unit. Now, for this one, we got three big ideas. The first one, objects and systems have properties such as mass and charge. So you have big idea one gets used quite a lot. Big idea two, this is new. Fields existing in space can be used to explain interactions. Remember that a force is an interaction between two objects. So one of the models we have that helps us explain interactions or forces is to use fields. Big idea three, the interaction of an object with other objects can be described by forces. So we've seen that one. All right, learning goals. I want you to be able to calculate gravitational force on an object as, from the effects of a net force on objects and systems. I want you to be able to approximate a numerical value of the gravitational field near the surface of an object from its radius and mass. And I want you to be able to use the model for gravity to calculate gravitational forces involving orbits and things that do not involve orbit. All right, so gravitational force. They're exerted at all scales and dominate the longest or largest distance in mass scales. It's an attractive force. Gravity pulls things with mass together. And it is the weakest of the four fundamental forces. So as you're walking through the hallways with your friend, there's a force of attraction pulling you and your friend together. And you do not notice it because it's so small. Now, Newton was the one who kind of started to get the ball rolling on what exactly gravity is. And what happens was he discovered that the force due to gravity is proportional to the product of two masses, and that it's inversely proportional to the square of the distance between the two. So here's what Newton discovered. Okay, R. That is not for radius. R is just some random position vector. So, for instance, if I had an X and a Y Cartesian coordinate system, and I had two positions, one at the origin and one somewhere out here, R would be the position vector from this first point to the second point. So don't always think that R is a radius. Sometimes R will mean a radius, but really R is for a position vector. In fact, it's kind of like a distance. The way we can say this is that being a force, we have to have a unit vector pointing in the R direction, which is somewhere out in space. That turns it into a vector. Okay, so since we have this proportionality, that means that there must be a constant of proportionality. And roughly 200 years after Newton, another scientist named Henry Cavendish discovered that proportionality constant for gravity. So, gravitational force then equals some constant times m1, m2 for r squared, and then I turn it into a vector by multiplying it by the unit vector. So gravitational force describes the interaction of one object that has mass with another object with mass. It's always attractive, and the magnitude. So if I want to calculate how strong it is, we have a formula. So what Henry Cavendish did for us was he gave us a number for that constant of proportionality. So this model then that G is really small. It's not that Newton could not find the constant himself. He was a very talented scientist. The problem was, at the time, the equipment wasn't sensitive enough to measure this. I mean, 6 times 10 to the negative 11th. That is a ridiculously small number. So that's why it took 200 years until we were able to get that number after 200 years after Newton. All right, gravitational fields. We think of these as a field of vectors. And we think of this vector field as a function of position, maybe time, the value of a physical quantity, and it's described by a vector. So they're represented by a lot of arrows. So for instance, let's say this is the Earth. Surrounding the Earth is a field of vector lines. And the density of those lines is an indication for how strong the field is. We give this a letter G, and when we're near the surface of the Earth, it's 9.8 newtons per kilogram. Now, as you get farther and farther away from the planet, because the planet's round, these field lines are radial, notice that the spacing between them gets wider. So what that helps us indicate is that the gravitational field becomes weaker. So this 9.8 number is only close to the surface. As you get farther and farther away, it becomes less than 9.8. And it turns out that it's actually the same relationship as gravity. It's an inverse square law. So let's say we have more than one source of gravity. So think about, let's say, a planet and its moon. So Earth and her moon. And let's say I have a satellite positioned somewhere between them. This satellite would measure a gravitational field pointing towards the Earth and a smaller gravitational field pointing towards the moon. And what I can do then is I can take these two vectors, place them head to tail, and I can get the net gravitational effect at that point. So these are all vectors, and I would just use vector addition the same way I used for forces. I would resolve them into their x and y components, and then go from there. So just simple vector addition. Conversely, a known vector field can be used to make inferences about the number, the relative size, and locations of the sources. So if I have a satellite out in space and it measures these gravitational fields, it can say, oh, there are three sources, one is stronger than the rest of them, and go from there. The vector field itself will surround the planet, and it's always converging. It's always pointing towards the source. So a gravitational field at the location of an object with some mass causes a gravitational force of magnitude mg. We've seen this before. This is how we calculate weight, to be exerted on the object in the direction of the field. So if I take a look at a gravitational field, it causes a gravitational force, and the gravitational force always points in the direction of the gravitational field. So if I have an object, and let's say there are these gravitational fields. When I put these all head to tail, I see that the net gravitational field is pointing in that direction. So the gravitational force will be pointing in that direction. So if this were a satellite, that would be the direction that it would be pulled towards. All right, so on Earth, gravitational force is called the weight. So the gravitational force is equal to how much something weighs, which equals mass times the gravitational field. So the gravitational field at a point in space, we measure it by dividing the gravitational force exerted by the field on an object by its mass. So again, a gravitational field would equal a gravitational force divided by mass. Now notice this leads us to a new kind of mass. Earlier we talked about inertial mass. This mass is different. This is gravitational mass. Alright, so now if the gravitational force, if it's the only force exerted on the object, then the free fall acceleration of the object will be equal to the magnitude of the gravitational field. So here's what that means. We have this relationship here. So let's say we're standing on the planet. This gravitational force would be capital G, mass of the planet, times your mass over r squared divided by your mass. Your mass would cancel. So I would be left with G times mass of the Earth. Now if you're standing on the surface of the Earth, that r becomes the radius of the Earth. So, and it would be in some sort of r direction. So G, we can find that by taking the universal gravitational constant times mass of the Earth divided by the radius of the Earth squared in some sort of direction. Now we can look all these numbers up. We can look up the mass of the Earth, we can look up the radius of the Earth. What it comes out to is 9.81 newtons per kilogram, which you would recognize as the acceleration due to gravity. So this helps us do some calculations pretty quickly, but it's only true when you're close to the surface of the Earth, near Earth's surface only. When you get farther away, the inverse square law kicks in, and G starts becoming much, much less than 9.8 very quickly. All right, that's going to conclude this video.